Give it a second. Sometimes when it does this, it's already recording now, and I'm just standing here like a goofball. So, all right. So we'll go ahead and get to it. So this will be lesson 1.5. Kind of pairs well with what we did yesterday, 1.4, which was solving equations. And we're going to use kind of those same properties of equality we learned or reviewed yesterday when we're solving inequalities. All right. So our learning target for the day is that I can use properties of equality to solve inequalities. So very similar to what we did yesterday, like I said. But just like a fundamental difference between like your typical equation that you would solve versus your typical inequality is that most inequalities have infinitely many solutions, right? So what's like a way like we can express our answers to show the infinitely many solutions? So like in other words, like a lot of inequalities will say solve and what? Anybody remember? Graph, right? So we kind of show that on a number line sometimes. There's also interval notation that we might show, but all that kind of differentiates an inequality from an equation. So while there are some similarities, there are also some differences, right? With that said, let's go ahead and get to it. All right, so what is the solution of 3 times the quantity x plus 2 minus 5 is less than or equal to 21 minus x? All right, so let's start by trying to simplify that left side of our inequality. So we'll distribute first. Get 3x plus 6 minus 5 less than or equal to 21 minus x. Combine like terms. 3x plus 1 is less than or equal to 21 minus x. Now I'll go ahead and get my kind of like terms to the same side. So I'm going to add x to both sides. That'd give me 4x on the left side and 0x on the right side. Let's go ahead and just so we save ourselves a line of work as well, go ahead and subtract 1 from both sides in this step also. So that's going to give me 0, 4x plus 0 on the left side, and it's going to give me 20 on the right side. So we have 4x is less than or equal to 20. Now we're ready to go ahead and divide both sides by 4. And so we get 1x is less than or equal to 5. 1x is less than or equal to 5. So at this point, we are solved. So this is one way to express all real numbers less than or equal to 5. Another way would be to graph it. So I like you guys to show kind of 3 numbers on your number line. So our boundary point being the middle one. So in this case, we would show 4, 5, 6. Then you have to decide. So our boundary point is 5. So remember, there sometimes we do like a closed circle, or sometimes we do an open circle. Anybody know which we would do in this case? You can just blurt it out if you know. Open or closed? Closed. Why is it closed? Because it's or equal to. So that closed dot indicates that 5 is a solution. Okay. So I like to do that above. Some people do it on the 5. I don't really care. So closed dot on the 5, and then we shade the numbers that are less than 5. So that'd be to the left of 5. Okay, so again, just kind of reading the graph, that tells me that if I plug 5 in, I should get a true statement. If I plug in 4.75 or any number to the left of 5, I should get a true statement, okay? Or if I plug in 6, I should get a false statement, right? So that's kind of what that means. So that's all we had to do right there was solve and graph. I want to go ahead and remember if I showed this or not. I guess I didn't show this yet. We'll get into interval notation and stuff later, so we'll just save that. You guys try the next one. I'll give you about a minute and a half. Just get as far as you can. You got 2x plus 4 times the quantity x minus 2 is greater than 4. So try to solve it and graph it if you have time. Feel free to compare answers, because sometimes, remember, I'll call on you after a work time. And these can be a little bit harder to check than typical equations, because a lot of them do have infinitely many solutions, and you can't check infinitely many solutions. But you can get a pretty good idea by plugging in a number or two if you have the right solution. All right, so just give me the solution if your name comes up that you came up with. He's not here. Let's try Catherine Stewart. What'd you get? You got what? X is greater than 2 is correct. Very good. So this is our solution. X is greater than 2. Also known as, or we could show it as, that'd be an open circle on 2 and then everything to the right of 2. Okay. So if you had any trouble, here's how we get there. So distribute the 4 first. Combine your like terms. Add 8 to both sides. So at that point, we're ready to divide. And of course, 12 divided by 6 is 2. Okay. So anybody have any questions before we move on? All right, let's keep moving. Okay, so now we are going to be reminded of what happens when we multiply or divide both sides by a negative. What does happen? Anybody remember what happens to the inequality symbol? It flips, right? Less than becomes greater than or equal to becomes less than or equal to, and so on and so forth. All right, so let's go ahead and work this out. So we'll distribute first like we did on the last one. So 2x minus 3x plus 3 is less than x plus 5. That would give me negative x plus 3 is less than x plus 5. All right, so I guess if we want to flip, and you could avoid it here having to divide by a negative if you add x to both sides, but just so we can see the example, we'll subtract x from both sides and get negative 2x on the left side. Let's go ahead and save us a step here and subtract 3 from both sides as well. That's going to give me less than 2. So negative 2x is less than 2. And again, if we would have gone the other way there, we would have had negative 2 is less than positive 2x, which would have been fine. But anyways, we'll go ahead and divide here. And as soon as you divide by a negative, I say that's got to be your first thought. Go ahead and flip that symbol. And then we get 1x is greater than negative 1. 1x is greater than negative 1. Okay. So now we will graph it. So on our boundary point, that's going to be an open circle because -1's not included, and then we shade everything to the right. So just a side thought, and I wouldn't necessarily write this out, but what I was kind of talking about earlier is, say we, say at that second line here, say at this line we decided to add x to both sides, what we would end up with there, like I said, don't write this out because it'll get cluttered, but what we would ultimately end up with is 2x on this side and -2 on this side. So then we would divide both sides by 2, and we get -1 is less than x, which means the same thing as x is greater than -1. Okay, so you see it doesn't really matter which way we go. You do the algebra right, you're going to end up with an equivalent solution. Okay, any questions? All right, you guys try the next one. Let me take that down to 1:30. I think that was plenty of time for you guys. All right, so guys, as you get finished, what I did on this one, instead of calling on you guys, is I worked it out on the board while you guys were working. So you can double check your solution against mine and kind of see if we have any questions that way. Anybody got anything? Everybody's good? Okay, moving on. All right, so like I kind of talked about, every example we've done so far has had infinitely many solutions, right? But sometimes, just like on an equation, you can have like the whole number line be the solution set, or it's always true, or it can be never true. Okay, now just to before we do these, just to recap kind of what we reviewed yesterday about equations is, if I have the exact same coefficient on opposite sides, basically then I'm just looking at the constant, right? If I have the same constant, it's IMS. If I have a different constant, it's no solution, right? This one, though, is not exactly like that. You have to, on this one, it matters what the inequality symbol says, right? So you're evaluating at the end, once once the variable terms cancel out, then you're looking at, do I have a true or a false statement? So let's see what I'm talking about here when we work this example 3, okay? So I'm distributing the 5 on the left side to get 15x minus 10, and then the 3 on the right side to get 15x. So there's your red flag moment. If I have 15x on both sides, I know this is one of those special cases, and then plus 9. All right, so if we subtract 15x from both sides, what we end up with is -10 is less than or equal to 9. Okay, now we know if -10 and 9 are not the same. So if this were an equation, this would be no solutions, right? But as we read what we have on the paper here, -10 is less than or equal to +9. Is that true or false? That's true, right? This is a true statement here, so this would be an always true, an always true. So if we were to graph this one, if you were ever asked to graph this one, it would just be you could graph any part of the number line and just arrows going both ways, right? That's how we would show that. It's the whole number line. No matter what you plug in, you're going to get a true statement. Okay. So any questions about that? All right. Go ahead and try the next one. So you should get a sometimes, well, probably a never and always, but go ahead and give you like a minute on this one. Bless you. Probably call on you guys for this one, so maybe compare with a neighbor. Greater, it's loving you today, man. What'd you get? Never true is correct, so good job. Here's how we know. So obviously distribute, get 4x minus 4 is less than or equal to negative 8 plus 4x. Subtract 4x from both sides, then we have negative 4 is less than or equal to negative 8, which is false. Okay, that's false, so that's a never. Okay, and sometimes those negatives can trip you up, right? Because sometimes we might think 4 is less than 8, but just kind of keep in mind we're talking negatives there. Any questions before we get to the compound inequalities to finish up the notes? All right, let's go ahead and finish them up then. The last thing we'll cover with this lesson are the and or inequalities. So these are kind of have segmented parts of the number line. So let's just kind of see what they look like. So this one is an and we know that because it says and, right? So basically, if it's an and or, if it's an or, you have basically two separate kind of inequality parts to the inequality to solve. Okay, so we have a minus 3 is less than 3. So let's go ahead and add 3 to both sides to solve that to get a is less than 6. And we have a two-stepper on the other side. So minus 5 to both sides gives me negative 3a is less than 3. Divide by negative 3, so we flip the inequality to get a is greater than negative 1. So a is less than 6 and a is greater than negative 1. If it's an and inequality, you actually want to combine those two to kind of be together. So we're going to combine into one kind of smooth answer. And you might want to note that this is 4 and only. In other words, you don't do this for an or one. All right, so what that looks like is basically your lower boundary always goes to the left. So we put negative 1 here. and then it's always less than your variable, and then your next one's less or less than or equal to, and then your upper boundary. Okay, so that's how you express your final answer on an and. Okay, and if you read that variable first, it still says a is greater than -1 and a is less than 6. So let's go ahead and graph that. So greater than -1, so that's going to be open on -1. It's going to be open on +6, and then we're going to shade in between. So just that small part of the number line there, right? So let me ask you this before we move on. How many solutions are there between -1 and 6 if we include the whole number line? More than that. Infinitely many, right? So there are even infinitely many solutions between like 0 and 1, right? So when you consider all the little decimals and fractions and everything else, right? So we still need to graph these, even though we're not showing as big a part of the number line. So that's where math that's where math can kind of make your head hurt when you think about there's infinitely many numbers between 0 and 1, right? It's just kind of cool stuff that you see in math. All right. Anyways, let's do an or together, and then you all will try one to finish it up. All right. So this one says, 5 minus 2m greater than or equal to 21, or 4m minus 1 greater than or equal to -21. So let's go ahead and solve both. Minus 5 to both sides. On the left one is going to give me -2m greater than or equal to 16. Divide by -2 is going to give me m less than or equal to -8. On the other one, add 1 to both sides, gives me 4m greater than or equal to -20. And divide by 4 gives me m greater than or equal to -5. Okay, so you don't combine these, you just literally use the word or, okay? So m is less than or equal to -8, or m is greater than or equal to -5. So let's see how this one looks, because it does look different. Let me make my screen a little bit smaller so we can fit everything there. So less than or equal to -8, that's going to be obviously closed on -8, and we shade to the left, okay? For greater than or equal to -5, that's closed on our boundary, -5, and then shade to the right. So that's how an or is different than an and, right? So an or is like pretty much the whole number line except for, this little space right here, right? So an or usually will cover more of the number line, right? It goes out and away, whereas an and is in between, okay? Any questions? All right, so you guys try one. That'll finish us up. I'll probably work this one while you guys are working, so you can just check as you finish. We have 7w plus 3 is greater than 11, or 4w minus 1 is less than or equal to -13. Looks like you do get some funky kind of solutions here, but that's okay. Or at least one. All right. So kind of put it all up there. So, you can see I kind of flipped it around at the end. So just to kind of review what I had, W is greater than 8/7, which is, just bigger than 1 at my boundary point. Or W is less than or equal to -3. I didn't have to flip it around, but, I like to have my lower boundary kind of on the left and my upper boundary on the right. That wasn't necessary. I don't think you technically have to do that. With an and, you would. With an or, not necessarily. Okay. And then the little details on the graph. Notice that my left boundary is shaded and my right boundary is open. Okay. So, any questions before we kind of take our break? All right. Let's go ahead and take our break then. We'll do let's do 3 minutes and then I'll post your assignment. Yeah, just sign out.